Okay. So the idea is to perform an introduction of molecular dynamics. And I ask if anybody has a question, can interrupt me and do a question. I prefer to do this. Once you see and you do not understand, please ask me. And before talking about molecular dynamics, I make an option to introduce some concepts that are important, why we can use a classical force field, for example, to understand interactions between the molecules. So then that's why I'm going to present some small overview about quantum mechanics. Yeah, about quantum mechanics for isolated molecule. Then I'm going to present briefly techniques to molecular simulation, include also molecular dynamics, this is the main topic, but also a small 2 slides about Monte Carlo. And then I'm going to talk about the classical force field, what's the property, how we use and how to select. And then I will talk about several algorithms of molecular dynamics, including integrators, thermostat, barostat, and several options that we need to perform in the input of molecular dynamic code to tell the code what to do, okay? So then I believe that everybody here had already a quantum mechanical course, and we wanted to study molecules or solids, and the main topic is to solve the Schrödinger equation, the non-relativistic one. I here present the Schrödinger equation in the time-dependent version. Here, when I presented these I'm meaning that we are looking to the coordinate of the nucleons and to the electrons, and T is time, okay? So then when we think about the Hamiltonian, we have the kinetic energy of the nucleons, kinetic energy for the electrons, interaction between nucleo and nucleo, nucleo-electron, electron-electron. And we can write the Schrödinger equation in the stationary way. What means that when we solve the Schrödinger equation, we are looking for equilibrium properties. Okay, once we have the Oppenheim approximation, the idea is that we can separate the movement of the electrons and the movement of the nuclei. And then we make all the geometry of the nucleus fixed, and we solve the electronic Schrödinger equation. When we think about that, we need to start a calculation with fixed position of the nucleus. So it means that we are going to solve the electronic structure depending parametrically from the position of the nuclei. Okay, if we change the position of the nuclei, we need to solve again the Schrödinger equation to see the electronic part. So it means that this E represents the electrons. We have the Hamiltonian that has the kinetic energy of the electrons, the interaction electron-electron, interaction electron-nuclei, and also the nuclei-nuclei interaction. And when we have the energy here, we are going to have the energy of the electronic system. So when we think about this energy, we can construct a potential energy surface, meaning that we are going to assume the adiabatic approximation, meaning that for each position of the nuclei, the electrons are in equilibrium and we have the energy. We change the position of the nuclei, we have another energy. So then we can construct a multidimensional surface where we can find the minimum, and all this minimum will represent the most probable structure that the molecule can have. If you find a total minimum, you say that's the most probable position. But if you take a look on this equation, we have no temperature on that, no temperature concept. And then when we perform ab initio calculation, most of the time, we are looking for the minimum. We are looking to the optimized geometry. So, but when we started to look to the quantum mechanical part, now we have several methodologies where we can solve the Schrödinger equation. we have semi-empirical methods, we have Hartree-Fock, and several other methods too, because in Hartree-Fock, we lose the electron correlation, and then we can put methods that after Hartree-Fock solution, we get this correlation between the electrons, and also we have density function theories. So this was the subject of the last workshop that we had, and the idea now is to implement this methodology. We have several codes that have the methodology implemented, and the idea is to calculate the electronic structure and the electronic properties. And most of the time, we look in the optimized geometry. But then to execute a quantum mechanical calculation, I know that everybody here already did a quantum mechanical calculation, we need geometry, we need basis set, and we need to have the method that we are going to use to solve the Schrödinger equation. So it means that we have at least 3 options to do, only 3 decisions, the geometry, we can start our quantum calculations. But then I'm going to show some examples, these things that we can do with quantum mechanical. For example, if anyone wanted to study in detail methodologies, look and understand what the ab initio calculations program they perform, I suggest here some books that are very traditional one. And I'm showing here, for example, one calculation that we perform in our group by Leandro with a ruthenium complex. This molecule is a catalyst that is used in water splitting process. And if you take a look, this molecule has 55 atoms. We performed the calculation with around 880 basis sets. It means that to optimize the geometry, we took around 2 days in a computer that has 80 processors, okay? To calculate the absorption spectrum, meaning that now I need to calculate also not only the ground state, but the excited states, we expend around 2 days to make one single calculation, okay? So if now we wanted to make a molecular dynamic simulation and sampling this molecule in a thermodynamic equilibrium, meaning that I have a specific temperature, specific pressure condition, I needed to see the molecule moving. So if I'm going to calculate the absorption spectrum or the band gap, has no sense to make only a single calculation in the optimized geometry. You need to sampling the structures and perform several ab initio calculations and have the average. So if we are going to average, for example, in 100 configurations, we spend 2 days in one single calculation, we are going to spend 200 days performing the absorption spectrum calculation. So that's why we need to have computers with several CPUs and parallelize the entire system to perform it. And here I'm showing what is the absorption spectrum of this compound in vacuum, the isolated molecule. You can see here, all these bars are the excitation energy that we calculated, and this is the intensities. And the line is the experimental data. And all these calculations, we perform 100 calculations with this molecule surrounded by the solvent. So then we have the solute, we have the solvent, we performed all this calculation, and we can convolute and have the good agreement between the experimental and the calculations, and we can now identify each orbital are participating for the excitation. So we are not looking the gap, the HOMO-LUMO difference of energy. We are looking the orbital that are involved in this specific band that are going to absorb light and cause the water splitting or the oxidation.
You mentioned that you, for example, for those really have like 200 configurations.
Yes.
Normally, how do you select 200 configurations when you have like 50 configurations? Because you are doing any calculations to generate them.
Yes, I believe that somebody is going to talk about the autocorrelation function of the energy. In our group, we perform the calculation of the autocorrelation function of the energy of the system. We calculate the interval of time that we lose the memory in the statistical sense. So if you have, for example, 1 million configuration that you generated, you can calculate how long is the time to your system lose the memory and have a statistically independent configuration. So typically in the molecular dynamic, we select one configuration per 1 picosecond, okay? So if you want to have 100 configuration, in minimal, you should have at least 100 picosecond simulations. Okay, so this is the idea. Okay, so once you understand that when you have the isolated molecule, no temperature concept, you can deal with the optimized geometry. Now, if you think about the thermodynamic condition, all your atoms are moving, and you need to take this in consideration if you wanted to have the temperature contribution, okay? So then when you start to think about the difficulties of performing quantum calculation, if you wanted to study a large system like soft matter or even a porous solid and things like that, if you wanted to have, for example, your system in solution, you will start to have to calculate systems that have around 100 or 1,000 atoms. Or if you go to a polymers, you are going to deal with around 100,000 atoms. Or if you're going to system that have self-ensemble and stick together in clusters. So you are increasing the size of your system. And I show you how long it will take to perform a calculation with only 880 basis sets. If you go to a large system, then your quantum mechanical calculations start to be very expensive. You need to change and go to a more simple system. So additionally, when you think about the size of the system, now your energy, potential energy surface become more complex because in each X, you should have 1 degree of freedom. And then for a large system, you have so many degrees of freedom. And then we ask you, why you decided to put the molecule here and not there? And then most of the people, we started to select by random configurations. So the idea is not to find configurations by random choice, but we perform some smart decision, looking the most probable configurations to find the positions of the molecule, one related to the other. And then if you have this for large system, it becomes much complicated. Every time that you increase the size of the system, you increase the amount of the molecules. Okay? Another difficulty that we have, oh, he is not good. Okay. Another difficulty that we have that, in principle, a Schrödinger equation has no information about thermodynamic condition. We can, even though, have information from that. What we need to think about it is to think about the ergodicity principle. What does ergodicity tell us? That if you wanted to have an observation property that you can measure, you can think that this property is an average over time or an average over ensembles. This is the idea. So then I can think, okay, if I can solve the Schrödinger equation that has time evolution, I have a trajectory, and then I can have the average, and then I can have the thermodynamic information. So, but the problem is that when you look to the Schrödinger equation, time-dependent, you are going to do the evolution of the wave function of the electrons and the nucleons. And they have a completely different time scale. So it's not possible to perform the solution of the time-dependent Schrödinger equation to try to generate trajectories for the nucleons. In general, you see time evolution of the electronic state, but not the nucleons. So the idea here is that we can build a methodology we call ab initio molecular dynamics, where we solve the Schrödinger equation, we calculate the forces between the nucleus involved in the electronic state, and then we solve classical Schrödinger equations to calculate the acceleration of the system. So the idea is solve a Schrödinger equation in the electronic state, calculate forces on the nuclei, and then now we use the classical equation of motion from Newton's law, classical one, and calculate the acceleration and make the movement of the nucleus, okay? So in this case, in general, the integration of this equation is performed in time steps that are around 2.2 femtoseconds, okay? And now this methodology is called first principle molecular dynamics. So in general, you have nowadays two kinds of first principle molecular dynamics. One is based on the Bohr-Oppenheim molecular dynamic, is the bond, or Campanello molecular dynamics. So in this case, what we are going to do is to solve the Schrödinger equation, calculate the forces on the nuclei, and then evolve the position of the nuclei based on the Newton's law. So it seems that's some kind of semi-classical approximation, because the movement of the nucleons are classical, but the force is coming from the first principle. Okay? If anyone wanted to study more about the ab initio molecular dynamic, I suggest this book here. Okay? It has many details, how to solve, how to generate the approximations. But typically, this kind of dynamic is very expensive. Because if you think about a system that you have around 100 or 1,000 atoms, in general, you cannot have simulations less than at least 60 picoseconds, okay? Because the scale of tens of picoseconds is the scale of the arrangement of the nucleons. So if you have less than this, you can see anything. You have at least that. And if you have a time step of 2 picoseconds, I'm showing here one example. We perform chlorophyll C2, is this molecule here, in around one solvation shell of 120 methanol molecules. So we perform the bond, Bohr-Oppenheim molecular dynamics. In general, if you have a system with a processor with 440 processes, we can calculate around 0.3 or a half picosecond per day. This is the typical calculation that you can perform it, okay? And if you think about that, if you are going to have around, in this case, 800 atoms, we have 40 picoseconds, we spend around 120 days, okay? And then you think, okay, now I'm going to run in a 2,000 processes. No, the program does not scale easily with the number of the processes, okay? We have nice scale until 100 processes in all the kinds of programs that we have available. CP2K, for example, is the program that we use in our group, okay? So here and here. There. Yes, it is. So if you are to use it, how? If you put there, for example, in the Gaussian option OPT, you are going to have the optimization. You are going to have the forces calculated in each step. You can ask, for example, do only one calculation of the gradient, and then they give you. Okay? Yeah. It's the ab initio calculation. It's the same calculation of the forces that you have on the geometry optimization. Not only that you go all the geometry optimization, but you calculate only one step to have one movement of the gradient. And then you change the position of the atom, go again, go again, go again. Okay?
On the initial, you have an analytical expression for the forces.
Ah, no. Okay, no. Yes. 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 Yeah, it has several advantages, because when you say all the time first principle methodology, mean that you have no single one parameters. So when you decided to do a vacuum calculation, you decided to have the geometry, the basis set, and the method. Here is the same thing. You decide the geometry, the method, and the basis set. And you tell the program, of course, if you are going to use periodic boundary condition or not, if you are going to have in the NVE ensemble, meaning the grand canonical ensemble with constant energy, or if you are going to add a thermostat, but you have no, in principle, parameters involved on that. So you can think, okay, then I have the exact solution. But you have the solution for the method that you decided. In nowadays, the cheapest one are the semi-empirical methods or the density functional theory. But if you decided for the wrong functional, you have garbage as a result. Okay? So you need to think about what kind of functional I need to describe good interactions of my systems. And then you need to use that. That's why when you decided to do ab initio molecular dynamic, you need to test several things. One is your initial condition, because you need to have a geometry. If your geometry is too far for the equilibrium, you need to expend much longer time than 60 nanoseconds. Okay, then what we do in our group is we perform a classical molecular simulation, select one structure, and then go to the ab initio molecular simulation. You guarantee that you are already okay in the initial condition. But also you needed to understand if your total time was necessary to see the evolution of your system. What you wanted to calculate, I don't know, but you need to see if the time is enough. And another thing, the basis set that you select. Most of the time we put a poor basis set to have a faster method. But is your basis set enough to describe a good geometry of your system? So you need to know also that. And the methodology. For example, if you try to understand the system that van der Waals interactions are very important, you cannot use a functional that has no van der Waals interaction. See, and then it's not enough to decide it. You need to make tests and prove that your options are okay, the size of the box are okay. Because sometimes people say, okay, I'm not going to use this program because there is no periodic boundary condition. I want a periodic boundary condition because I wanted to describe a liquid. But if you take a look at the distance here in this side and in distance here on this side, perhaps if your box is too small, this molecule is interacting with the two sides of the molecule. So you have a completely wrong structure of the first solvation shell. Then periodic boundary conditions, they are important, but you cannot use a so small system. You need to have some space. And then you say, okay, then I'm going to turn off. I'm not going to use the periodic boundary condition. Okay, then you need to look for the diffusion of your system. Because sometimes, for example, we did the simulation of phenol in water, okay? Phenol is mixable to water. But when you perform ab initio calculation without periodic boundary condition, all the waters goes to one side, and the phenol make one hydrogen bond with a bubble of water. And the phenol is not in water, because the aromatic ring does not like water. So then it's important to take a look, to see your trajectory, see if what you wanted to describe is the correct answer that you get it, okay? So it's not a blank thing that you decided and look at the result. You needed to take care because you decided a lot of small things when you decided to do even ab initio molecular dynamics, okay? So then what we have, in fact, we wanted to describe dense system, a lot of molecules. So if we think about that, it's important to think that if we need a lot of molecules inside your system, you need to have statistical mechanics. So the idea is to perform simulation. And the first methods that we have to perform simulation, they were developed in the 50s. The small systems, the first simulations we have in 52, the first paper on the molecular dynamics. But only after the 80s, these methods become robust. they become with good agreement with the experimental data, okay? And basically we have two methodologies, the molecular dynamic simulation and the Monte Carlo method. With the molecular dynamic, we performed. This is a deterministic technique where we are going to solve the Newton's equation of motion, classical one, of any molecules that are going to interact by a potential. Okay, so in this case now, we are not more calculating the interaction using quantum mechanics, but we are going to have a classical equation that should map the interactions coming from the ab initio interaction, okay? And then we have a classical force field. I'm going to talk about this subject. And if you wanted to study with Monte Carlo method, you are going to have a probabilistic method. We are going to generate structures that come from the Boltzmann distribution with systems with n molecules interact with the same potential. So in principle, both methods can be the same, but in practical, not everything is like that. So what I'm going to show is that this is the ergodicity principle. When you think about thermodynamic, you can think about the kinetic theory of gas. So you study the movement of each molecule in a gas, make an average, and you have the properties like temperature, pressure, and so on. So if you think now, if I have a potential, I can calculate the gradient and generate the force. And then this representation here, each symbol represents the Cartesian coordinate of all atoms in the system. So if I calculate the forces applying in the Newton's equation, I'm going to see the movement of the atoms. And then I can follow the trajectory of the system. And if I wait long enough, I will visit all the possible configurations and I can perform an average. Okay? In the same way, I can think about statistical mechanics and think, okay, each configuration has an energy, and I know that in the thermodynamic equilibrium, I need to follow this distribution, the Boltzmann distribution. So then I can generate structures randomly, calculate in the Boltzmann weight of each distribution, and generate structures with this distribution of probability. So then the Monte Carlo, you are going to generate a structure, but not following a trajectory, by random. And in the end, if you wait long enough, you are going to visit all the configurations. Both methodology are going to be the same. Okay? So with molecular dynamics, what we need to have it. The idea is that you are going to have a box, put all the molecules and atoms of your system, and set up the information with an initial position and initial velocity, okay? Now, with the positions, we can calculate the potential. With the potential, we have the gradient, we calculate the force. We know the mass of each atom, we calculate the acceleration. So, these equations that I'm showing here, they are the algorithm of velocity Verlet, okay? This algorithm was suggested in 1982, but the first time that it's appeared in the literature is very old. The idea of solving the Newton's equation using this idea, or these equations, is in 1791. But Verlet made the first implementation in 1967, and the initial was the Verlet algorithm, and then evolved to velocity Verlet algorithm. So this algorithm is one of the two most used methods to integrate the Newton equation of motion. The idea is that if you take a look on this equation, this is what we learn about constant acceleration in the school, okay? Position is initial position, initial velocity time t, half of the acceleration time t square, okay? So then this is not the situation because we have no constant acceleration here. But then we can think on this equation that is the Taylor expansion, and we truncate it in the second term. Okay, so we can think that this equation is correct if I have an error in the next position. So then if I'm going to use this equation, I need to guarantee that the time step that I'm going to use, the constant acceleration is a good approximation. Okay, that's why when we use a molecular dynamic simulation, our time step should be very small to guarantee the precision of this approximated equation. Once you calculate, you have velocity, positions. With the positions, you calculate the acceleration. You calculate, you have all these terms, you calculate the next position. And then if you have now the next position, you can calculate the next acceleration. And then the idea of the velocity Verlet algorithm is that you could use velocity plus acceleration times t. But now what they do, they perform an average between the acceleration of this configuration and this configuration, has an intermediate acceleration, and we use that to calculate the velocity. So this method is a very simple method. You have only two equations to solve the Newton's law. The problem is that you have here a square times of the delta t. So if you use a very, very, very small, like attosecond molecular dynamic, you start to have errors in these calculations, okay? Because you have a square root, a square of a very small number that should be even a smaller number. So we started to deal with numerical problems to get this small number. So in general, if you are going to use the velocity Verlet, we suggest when you use larger delta t, not too small. For too small delta t, I'm going to present another method that calls leapfrog method that you are going to see that's more precise, okay? So then presenting all these things, you can see that I can have position, velocity, and acceleration, and now I have new positions, new velocity, new acceleration in another time step. So I'm constructing the trajectory of the system. But because we use the forces calculated from the potential, we are in a conservative system. Conservative system means that we have constant energy. And then if you take a look in the natural ensemble of the molecular dynamic is the number of particles constant in your box, the volume of the box constant, and the energy constant. So most of the experiments are not performed on this ensemble. They are performed in the temperature constant ensemble. So we needed to change the ensemble. And the idea is that if I wanted to have a constant temperature, I needed to couple to this system a thermostat, okay? And then I'm going to put energy in the system, take off energy of the system in the sense that we have a constant temperature in average, okay? I'm going to come back and talk about the thermostat, what options we have. So the idea now is, if we decided to use Monte Carlo, what we need to have? So the idea is, the Monte Carlo is built on the idea that we need a Markovian chain to change from one configuration to the other configuration, and this chain should agree on the balanced data. It means that if you have a configuration and the probability to change to another, you have the same probability to be in another and come back to the same. So two configurations, they should have the same probability of exist and probability to change. So if I multiply the probability of Boltzmann and a factor that make one conformation go into the other, I need to have the balance of the two conformations, okay? So then, if I find a method to build up this construction, this is the acceptance criterion. I have positions. I change this position randomly. I calculate the energy before and after the movement and calculate the difference of the Boltzmann weight. If I have this and the energy goes down, I accept. If the energy goes up, I reject. So this is a very simple method. We can perform that, and now you have a new position. What's the advantage of that? Because I have only a single calculation to perform. I don't need to calculate the gradient, generate the force, and then solve Newton's equation. I only need to calculate the energy. I calculate this term, and so. What is the disadvantage? That I lose the concept of time. I do not have any evolution of time. I generate structures that are acceptable, that has Boltzmann distribution. I can do averages, But I cannot, for example, calculate the diffusion, because diffusion is a time evolution of the movement, okay? So then when I think about that, another advantage of use this methodology, because in the Boltzmann weight, I have constant temperature. So I do not need to couple a thermostat in the system to have constant temperature. So I don't need to have a large system to have a good average to calculate temperature. Okay? And then this is the best way if you want to introduce temperature in a small system.
Regarding molecular dynamics, if you have many molecules or atoms, you have actually chaos. It's a very complicated system, and you don't reproduce the real trajectory.
No, you see, you.
Why can you use it for calculating, for example, high dependence? Because you are not really solving the initial equations, because you are not reproducing the.
You can tell that's a very acceptable criticism to the molecular dynamic, that the trajectories are not real because you made the approximation in the Newton's equation. That's correct. But in the end, what you have in the ab initio, in the molecular dynamic simulation, that you are generating structures, follow a dynamics with a conservative force, and this stayed in an ensemble. So then you guarantee, yes, you don't need to have correct trajectories. You need to follow that you are in a conservative system, your interactions are well described. So this is the key point of the molecular dynamics.
My question really is, but when you look for a movie, for example, of the atoms, you can gain insight about the system when you look at the particles moving, even though it's not the really
correct. Yes, we have. We have long experience from the 80s until today, showing that we can describe very nicely all the dynamic properties. How long a hydrogen bond can be formed and can be broken. We can see where they are, how your system moves, how it diffuses. And you have, once you have a good force field, everything is okay. So this is the key. The parameters. Yes. That's what I'm going to try to convince you, that we can build a good force field if you take care, if you look your system, if you make quantum calculations, and if you take a look. If you only put in a site and get the force field and use it, I don't know. Perhaps you have it, good decisions or not, okay? So I'm going to talk about that. So, but everybody understands here the difference of Monte Carlo and molecular dynamic. In principle, they can solve. Monte Carlo cannot have any information about the dynamic, but it's a much simple system, okay? So, and if you wanted to translate and rotate, this is the method that I show you. But if you wanted to study the formation of the molecules, this method is not very good efficient. So that's why we recently implemented in our code, because we have the DICE code that performs a Monte Carlo simulation of the liquids, and we implemented with Henrique the bias Monte Carlo, where now we have a very good methodology to see the internal degree of freedom and the formation of the molecules, okay, with our code. So then going back to comparison, molecular dynamics and Monte Carlo, in principle, if all of them follow and see all the accessible states, accessible configurations, we have the ergodicity telling us that both are the same, but we have advantage and disadvantage. For example, molecular dynamic is good for large system. It can show us the time evolution of properties, but is not good, definitely, for conformational sampling. Why I tell that? Because we have experience, and we show in a recent paper that molecular dynamic, either ab initio or classical, cannot go through potential barriers larger than 6 kK per mole. So if you have your system, one change in conformation that has a barrier larger than 6 kK per mole, You are not going to sampling well with molecular dynamic unless you use enriched sampling methodologies. There is another kind of methodologies that you can put together with molecular dynamic, then you generate structures. But when you generate, you do not guarantee that you have the correct Boltzmann weight on these structures. So if you wanted to recalculate electronic properties, putting together, for example, 100 configurations that you generate with an enriched method, you needed to take care because one of them could have lower probability and the other one can have larger probability, and you are using all of them with the same probability. No, 6.
But if you have a large temperature,
yeah. No, if this is one of the enriched method of molecular dynamics is, for example, put 100 kelvins and you make your sample. Okay, but all these structures, they are going to have the correct weight for 100. Now, suppose that you wanted to calculate the average gap. You cannot use those because you have no guarantee that at room temperature, all those structures will show up. You are sampling, but... Yes, yes. So then put this number, 6, in your mind. If you make ab initio calculations and you have trust that your barriers are larger, 10, 20, 40, molecular dynamics can be not a good option, okay? I prefer to use Monte Carlo because you are going to jump these barriers. You don't need to pass to the barrier. You can jump from one configuration to the other without. We show in this paper of us that you can go from one configuration to the other if with a 40 kilocalorie per mole barrier. So it doesn't matter about your barrier. Only matter about the difference of energy of the configurations, okay? But molecular dynamics, no. You need to cross the barrier.
Okay. So then, your next step, based on the picture of the person.
Yes. Yes.
The Monte Carlo, you don't have that.
No.
But then you need to provide, to say, a smart way
Yeah.
how to move from one configuration to another.
Yes.
Means basically you are replacing one approach in which you are using the forces,
Yeah.
which is the exact one risk you have the correct force field, to the one in which you are they provide a smarter way to overcome this barrier by cooperate or something like that.
Yes.
That's right.
Yeah, that's why you say bias. Because when you say bias, you say, I'm going to select the best one. I guarantee that I follow the detailed balance. I guarantee that I follow the Boltzmann distribution, but I'm not going, because see, if I'm only go to the direction of the force, thinking that the equilibrium structure is there, one minimum, the other equilibrium structure is there, I want you to go there, but my force come here. So I only can go there if I have enough velocity to receive this force, but it's still going, and then I jump it, and then the force comes to this direction, okay? So I only have enough energy to go up if my kinetic energy is very high. And then the force can push me in this direction, but I still have movement to that direction, okay? So then that's the important point on the molecular dynamic. And Monte Carlo is good to conformation analysis, but all the methodologies that we have goes to apply to middle-sized molecules. I wanted to study a protein. Can I study protein folding with Monte Carlo? No, you cannot. Because the probabilities in the end, when you construct motions, you are doing with product of probability. If your system has so many degrees of freedom, in the end, your probability will be very slow, very small, and then you do not succeed, okay? So Monte Carlo bias Monte Carlo can be applied to half medium-sized system, not to large system. Yes.
For example, molecular dynamics, the complexity is quadratic. The Monte Carlo is linear. What is the order of the complexity of the ab initio? Ab
In general, if you choose a DFT method, is the number of electrons scaled by 5 power. So,
I don't understand. You said like you can't jump this barrier in molecular dynamics, right?
if the barrier is too high, if you have 4 kilocal, is easy. You go wherever you want.
I had this problem before. Even with Monte Carlo, like my system had you are like with,
You are talking about regular Monte Carlo, you also do not go. You need to have a better Monte Carlo, a smart one, a biased one. Okay? Regular Monte Carlo, you don't go also.
you kind of take care of it because still your PVT it's not large enough to jump the barrier.
Yes.
So you have to
No. You have nothing about the temperature. You have the idea of how you generate a smart structure. This is the idea. Not generated by random, but generating good ones. And we spend more time, of course, trying to see what is the good one. And then once you know, you go. That's the idea. Okay? So then I can other time, other course, talk more about Monte Carlo, but the idea is called molecular dynamic. What time is it now? Half, okay, that's okay. Okay, then let's go to ab initio force field, okay? The idea on the force field, on the classical force field is now that we can treat very large system with going to 1 million atoms, okay? We can go to large time scale. I'm talking about large, 100 nanoseconds, or even go to microseconds. So if you go to the literature, people are going to larger times on molecular dynamics with all atoms included, goes until microsecond simulations, okay? And the idea is, if I wanted to have large system, large time scale, I cannot use a very, very small time step like the ab initio molecular dynamic that I need. I needed to do some commitments here that I can increase a little bit the time step, okay? I'm going to talk about that, about the constraint methods. Okay, so then the interaction of two molecules, A and B, will be the interaction of the two atoms of each molecule. I use sum over all atoms in molecule A, all atoms in molecule B, make the pairwise interaction, atom-atom, and I will interact all the molecules, I will have the total energy of the system. So, but when I think about interact atoms that are bonded and atoms that are not bonded, I have different energy scales. That's why I build up a function where it can reproduce physical issues that I can measure, and I can reproduce physics information about using a constructed classical force field, okay? So then the idea is that if I have two neutral atoms together, I can calculate how it's the movement in ab initio. For example, the molecule of H2, O2, and 2. I can see the vibrational movement. So if I know that is a vibration, harmonic or anharmonic, I can have, depending on the temperature, I can build a classical force where I can have harmonic movement or anharmonic if I put more orders, okay, of the potential power. So the idea now is that I'm going to describe the harmonic vibrational movement between two atoms as an equation where I have two parameters. I have the equilibrium position. When I go to 0 Kelvin, what is the best optimized position in my ab initio? So is that value here. And now I have also the strength of the bond. If the strength is very high, the movement is small. If it's soft, I have a large movement. So this constant will define the frequency movement of this vibration. And this is measured by infrared experimental. So I can know that about the experiment. Go there and say, in O2 molecule, what's the vibrational mode? And then I put this constant here. So it's very simple, the parametrization, okay? If I have three atoms, also I will have an internal movement of open this angle and close this angle. I can have harmonically or I can have anharmonically. If I have, I write again an equation. Take a look that this constant here has different unit of this one. Because here I have angle, this is I have distances, okay? And now I have again the equilibrium position of the angle, I have the strength of the movement, and I can describe. If I have 4 atoms connected, now I'm going to have what we call the dihedral angle. That's the motion, the rotational motion of one atom compared to the other 3. Okay? If I have that, I need to have a slightly different equation because now I need to guarantee the periodicity of the movement. If I have 0 or 360 degrees, I have the same movement. Okay? And we can build up a series of cosine conformations or of cosine functions where I can have several minimums. So this n, this means how many minimums I should have in a period, okay? And then I can sum at least 3 or 4. Most of the potential force field, they can have until 6 parameters for this force. And I can build up several minimums with different energy relation, because I have here also another parameter. So in this case, I have 3 parameters. I have the intensity of the minimum or the barrier, I have the number of minimums, and I have a phase, because I can change the minimum wherever I want, okay? So if I combine 3 functions of that, I have a lot of flexibility to build up a rotational function. But how I should know if these parameters are correct or not? If I have a molecule, I go to ab initio calculation, I make the rotation, I calculate the entire energy to make the movement, and I compare with the classical force field. Then I know if all my movements are correct or not, or at least if they follow the correct trend. Okay? Because the most important is to have the well-defined minimums and the relations of the energy in order of magnitude acceptable.
You have a procedure, example like 100 picosecond of initial MD, run some type of algorithm, with double notation from that one to perform an MD calculation, use like lumps and droplets for any given type of material, solid, organic, whatever.
Juarez, I would say that there are some codes that perform that, but in general, they are not easily found. In general, they are not free distributed. You need to have collaboration with people. So what people are trying to do nowadays is to parameterize the coarse grain. For coarse grain, this is the state of art. They perform some ab initio small simulations. They try to have the best force field, and then they perform the classical force field for larger system, parameterize that to have spheres, large spheres, and then you go to another scale. But if you ask me, there are free software that I can download and use it? No.
It's not this type of, say, technology we need to be very important for all the region. Because we have several types, like UV, doing ab initio, but we need to build up a bridge with the dynamics. For example, I'm willing to pay very high for those ones that really do it.
We have some points here. The problem is, that I did not talk about. Once we decided to use a pairwise potential, I put this F. What it means? In the real ab initio world, we have a many-body interactions. Here we do not. So we are doing with approximation. You are trying to describe many-body interactions in 2-body interactions. When you perform that, all your parameters start to be dependent on the condition of the simulation. It means that if you enlarge the temperature of your system, you have no guarantee that the same parameters can be applied. And then if you generate a very sensitive method, like an ab initio trajectory, to generate the classical, perhaps you are mapping the system in a very small region of your phase space. So the point that we are dealing, that we have some errors here, that are in the order of magnitude that allow you to visit several places to make better approximation. And that's why you cannot be so rigorous on the potential. You need to have some errors. One of the errors that I'm going to talk about is about the charges. I'm going to talk about that. Let me get to the charges. And then that's why we need to be very awake, because we can construct a methodology that can generate to us a very good classical set of parameters that describe that region, but then in the real world, you did not sampling all the regions. And then you go to the classical, you are going to constrain the region that you are going to visit.
If you have one approach, you can make the data connection between initial dynamics with the classical force field of a large system and a large scale.
Yeah.
Even that we have a error that make like 20% of the statistics, okay? But I have a powerful tool, the way that's faster to screen large material, means we are able to accept a error like 20%. Because if I'm able to predict like 1,000 materials, and I pick up 10 the best ones, but I commit an error in 2 of them, but I have 8 that is good, means.
Let me tell you, I saw some conferences, people try to screen materials. And then they said, okay, I need to calculate 5,000 molecules, then I'm going to use a very cheap methodology, for example, semi-empirical, or a very simple DFT with simple basis set. Okay? So then they screen. In the end, they selected 10. They asked the experimental to synthesize the number of molecules that they accepted was 1 from 10. So the error is not 20, the error is 90.
Narrow the error.
Yes. Yes, yes, yes.
But if we are able to have a 10% of the question quality, the rate of success is low, I understand, but it's a better one, it's a better rate of success than without meet quantity. If you go to meet, we have 100% that is 0.
No. We have some strategy that I'm going to try to show here today that improve your chance. If you take attention for specific parameters of this equation, you don't need to parameterize everything. You need to take attention of 3 or 4 terms. They are the important one. So then you can decrease your error. Of course, I understand. You want it to. Yeah, build automatic thing that. Yeah. So, but I'm working on this idea is to generalize the approach, how to make the approach easier, and then we have some steps that we think that we are getting success on performing that. Okay. Yeah.
Those guys can use it to combine with London.
Yes.
And we are to say we are a team.
Yeah. That's what I think that's important to present seminar here, because we can discuss our progress. Because my group working on force field development of parameters to improve our chance of have good results compared to the experiment. Okay. Oi. Yeah.
This analytical formula is just few among different kind of materials.
Yeah.
Analytical forms.
Yeah.
Difficult to just translate.
Yeah, but I believe, Eldis, that in this kind of equation, we have some terms that we do not need to take attention for some specific kind of properties. For other properties, for example, if you take a look on this part here, and if you are interested, for example, in Juarez's kind of search, you are searching places where you should adsolve molecules in a nanoparticle. The internal bonds of the metals are not important to describe the structure of the surface. And then you can decide, let's freeze all the surface system and try to only the outsider. So depending on the system, we can have a very good, smart strategy. And I think that I have some clue about that, where we can invest time, for example, for ionic liquids, for nanoparticles, for solvents. So we can build a strategy different for each group, but work as a team, of course, selecting, yeah, this is the idea, okay? So I really need more time. Okay, so everybody understand what we have here as what we call bonded atoms, and we have also an additional term. This calls out of plane, because if you think in a ring, when you have 4 atoms, for example, benzene rings, imidazole rings, you don't want it to open your ring because this atom wants to do this kind of movement. So then you impose for your system movements that belong to a plane. You go up and down, but no more than this. So in this case, what you can do is assume that you have only 2 minimums, in general 0 or 180, one position or the other, and you make a very high barrier. So you guarantee that your system stay there. Or you put a spring and you make harmonic movement out of the plane. So this is the 2 main potentials. So once you have all these, what we call bonded potential terms, we are going to the further atoms. For example, if you have another atom here, how it going to interact with the first? Is no bonded anymore, because bonded go until the third neighbor. After third neighbor is not bonded anymore. So then you are going to have the interactions between 2 molecules, described by non-bonded, and the intermolecular interactions with atoms further than the third neighbor, the fourth neighbor and on. So when we have that, we are going to have 2 terms in general, the van der Waals terms and the Coulomb terms. And then in the beginning, I told you that we wanted to describe here with quantum mechanical ab initio for 2 atoms, equal atoms, okay? But in general, we are going to have 2 different atoms. So now what we have in the fact is that one atom has the electric affinity different from the other. So the electron is not well distributed in one atom and the other. You have a cloud, electronic cloud, that goes to more one side to the other. So it means that each atom will have a little more or a little less electron that should be. Okay? Then you have these atomic charges. And you are going to interact, to make the interaction about charge and charge. Each atom has a Coulombic interaction, okay? And if you think about Coulombic interaction, but you need also this van der Waals interaction, because when you do not have this charge-charge interaction, you need to describe 2 atoms that you cannot collapse one each other, so you need to have a repulsive term, and you need to have also a dispersive attractive term. If you put attractive term and repulsive terms, you make in a curve like that. So this is a very simple model to build up one minimum, one specific position. This is the parameter, the size of the minimum. The other parameter is the time, the distance that you cross this energy here. So you have 2 parameters and you describe the van der Waals interactions, most of them, repulsive and attractive, okay? If you put everything together, you are going to build up your force field. But I'm describing here the OPLS and amber force field. If you go to Grommax, charm, you can have additional terms. You can have, for example, not for the Coulomb interaction charge-charge, you can have dipole-dipole interaction. I can have more other functional terms for this term here, not cosine by n phi, but cosine square, or the number of the power law of the cosine changing also. I can have here the cosine of the text. I can have here the square of the distance. I have many different equations. So take a look on when you decided for a force field, you need to know your equation. And then you said, okay, I'm going to mix it because for this molecule, I only have onboard parameters. For this one, I have OPLS parameters. I will mix it. If they have the same equation, okay. But if they have different equation, it's difficult to mix them because they are not going to answer properly. Okay, then if you're going to mix, take attention on the force field. Yeah.
And you try, for example, two force fields describe the same system. They agree?
Depend on the molecule. You have it, depend on the molecule. You have, for example, the most used system for molecular dynamics nowadays that the people is massive utility is protein, okay? You have several papers where you select a family of proteins, you will study the conformation with several force fields, and in the end you compare. And then you say, for this class of proteins, this force field is better because agree with this experiment, or this, but this one is not good, and this one is much less. For water molecule, we will have at least 6 good parameters, 6 good force fields for water. And then you decide, because if you want to take attention to hydrogen bonds in higher temperature, low temperature, supercritical region, you should select different force fields for water. So the idea is that you can interpret all these terms. You can, in your system, understand each one is most important to get the water. You can try to build a good philosophy to get these parameters or to use parameters from the force field. But you have no guarantee at all that what you are doing are okay. That's why we all need experimental data. We all here need experimental data to, in the end, compare and say, see how good is my potential? I parameterize looking this property, but now I can describe this, and that. And then that's good parameter. But if I decided, and then I'm going to put together with the experimental data and say, okay, don't have it anything, and then your force field is not good. And then you can tell me, but how predictive is this methodology? It's good because you can train for a family of molecules and then apply small changes for other families. And you have a very nice confidence for if you work well on your parameters, you are going to have a very good answer for the system.
When you use the same parameters that you train in the book, I don't know, you measure the experimental data in the book, and you fit your parameters. And when you go to, for example, ionic liquids interacting in surface, you can use in principle parameters that you found in bulk regime.
In principle, yes, but in practical, no. Because if you understand that your system has a large polarization effect, bulk polarization is completely different of surface polarization. And if you have one comparison between volume and area that is very high, you need to be very attention. Because if the area is competitive to the volume, and then you need to take a look on the polarization of the surface, different on the polarization of the bulk. Okay, so
Serious issue because people sometimes fit parameters use a flow and then go to the surface, but it's not.
But see,
because the dialect will be that different.
But my point here is that you cannot decide, do not use because you do not trust. What you should to do, or what you should to do, is your homework and understand your system. What are the largest contributions? What I wanted to describe, and if I'm putting the correct ingredients on my calculation, this is the idea. So if I could only simply that, execute that, and in the end I have one number that's correct or wrong, no, it's not the idea. To build the force field, to have a good system, you need before to understand what kind of contributions you have. I am taking into account with this kind of force field. I need to change my force field. I have some parts that cannot be answered by this one. And then if you know that, you can construct a good model. So here the point is modeling, not use blindly a methodology, get the result am I correct. No, no, this is modeling. The modeling is here on the force field. This is the crucial point. Yes, yes. No belief that the inner sight can give you the correct parameters of your molecules. You need to test. You need to perform a initial calculation. That's why people that comes from the biology background, chemical background, that do not know how to perform a initial calculation, in general, they use blindly this kind of methodology. They can have good result or bad result, nobody knows. And that's why every good referee should ask you, how did you test your force field? You guarantee the validation or not? That's the key point. Before publishing, how I tested. I have confidence. I compare with what? I have experimental data. I do not have. That's why it's difficult when you think of an automatized methodology. But if you are looking to a specific set of systems, for example, ionic liquids, they have specific characteristics. Nanoparticle, metals, they have another one. Inorganic porous materials, they have another one. So, but each class of materials, protein, they have another one. Each class of system, you have some information that you should look to the experimental data and put information in your force field. Okay? Okay. So this is the key point. So going on, this is what people used to do. The choice of force field is crucial. But if you are working with molecules like solvent, biological molecules such as amino acid, nucleic acid, sugar, carbohydrates, lipids, you have a lot of experimental data. A lot. Then all these force fields, they should be very good for this kind of molecules. If you are an undergraduate student, ask me, can you give me a very simple model, and then I give you a protein? It's much simpler than my dye that has 50 atoms. Because with the protein, I go there blankly, take amber force field, use it, and all the setups, the tools that you can use is built to protein. But no. And now I want a catalyst, has a metal atom. So this is a nightmare. Because you need now to perform a lot of mechanical calculation and guarantee that you have a good force field. That's what Henrique tried to show when he used the Lick-Pargen or other. We try several ones. Every time that we read a paper and say, we have a site where we generate automatic force field, we go there and test it. Most of them, for very simple molecules, are okay. But for complex systems, they are not okay. Okay? And what we do in general? In general, we wanted to study inhibitors, sensors, dyes, anesthetics, or catalysts. And then we need to have experimental data, because if you don't have, we need to build up a methodology to take our parameters. In general, people consider that the intramolecular parameters, like the bonded and non-bonded parameters, they are transferable. All the force fields sell that idea for you. For example, the UFF force field, they have parameters for all atoms in the periodic table. And then you go there, you have parameters. So it doesn't mean that they work in all situations, because sometimes they are not transferable. Okay? If they are not transferable, my suggestion is that you can use the epsilons and sigma for the van der Waals. You can use the springs forces, but you cannot use well the charges and also the rotational dihedral profiles. These ones, you need to take a look on the ab initio level and see for your system compared to other molecules if you have different options or not, okay? So my idea and my suggestion is that use the van der Waals, use the springs, but take attention on the other parameters, okay? And now you can generate your optimized geometry with quantum mechanical calculation, make geometry optimization, or go to experimental data, get the equilibrium values of the bonds and the angles. You can calculate the charges using ab initio calculation, but the most important part is that you need to use a methodology that fit the electrostatic potential. So never use Millikan population, because Millikan populations are not built on the electrostatic potential. You need to have a good interaction of your molecule and other molecules, okay? So then make charges distribution based on the electrostatic fit. You can use HASP, ChalPG, Max-Coleman, you have several options. And in general, the suggestion of the force field that are compatible with the other information is that you use the Hort-Fox 631G star method to calculate the charges, okay? And why they suggest that? Because these charges are slightly overestimated in the dipole moment. Okay, if you calculate the dipole moment with a very good basis set, with a very good method for a molecule, you are going to have a very good dipole moment compared with experimental data. But when you put this system to interact with other, it's going to suffer polarization, and this method superestimate the dipole moment in around 30%. So this is an average polarization. You use that, people in general be happy, and that's all. Okay, but if you perform your calculation and see that your system is peculiar and has a larger polarization than 30%, then you should another approach to calculate the charges embedded in the environment. And the idea here is to analyze the torsional angles that you have the classical profiles and compare with the ab initio profiles to see if they, at least the minima, are well described, the amount and the positions of the minima and the relation between the energy. Because in the end, your sampling of configuration will follow the force field. If your force field tell you, okay, you are going to be in gauche plus position, but your ab initio tell you that you are going to be in the trans position, it's better if you change from trans than have the gauche position, okay? So this is the idea. Going back, I'm showing here, for example, this is the central part of our MOF nanoparticle that we are working. This is the work of Alexander. We have a zinc in the middle. We have imidazole here. This imidazole is not protonated. This one is protonated. So we have for substitution. And we have the label of the atoms, the charges, epsilon sigmas. We have here the nickname for each atom. We have all the bonds, parameters, angles, torsions, dihedrals, impropera, out of plane. So we have a lot of numbers, and now we can start the simulation. The example that I wanted to show you, that's how delicate are these numbers. Here, we performed the simulation with the 4-pyrimidine without any protonation. We take the force field suggestion in the literature, and we can see that all these imidazole rings, they are very rigid. They have some small movements, but they do not have bending movements. So we add one hydrogen here. The only change that we performed were adding a hydrogen and changing the charges of the nitrogen that is connected here. Oh, here, okay? So before, all the nitrogens, they have this charge 0.5, and now here, all they have charge 0.5, negative, and when we add the charge of the hydrogen, we have now this atom with charge 0.32, and the hydrogen with charge 0.32, positive and negative. And then you can see that the internal movement of the imidazole is a lot flexible. So we only add one atom and change the charge distribution. And now we introduce a larger flexibility in the ring, because the ring was constructed to have repulsions and attraction that follow that charge. When we change the charge, we include flexibility. So then, if this flexibility is okay, but if it's artificial, I need to correct. Okay, so this is the basic idea. We can do this for several complicated molecules. We rotate, for example, this angle here, calculate the ab initio one, compare with our parameterized force field, then we generate a lot of angles. We can do that. And for example, I'm showing here some simulation where we have molecular dynamics simulation. Here we are simulating a peptide. We have around 11 amino acids. All in blue, we have amino acids that are polar or charged, and these in green are unpolar and uncharged. And we put this peptide in a phospholipid bilayer, and we can understand the interaction of this phospholipid. If you take a look on this kind of simulation, Leandro is my student who worked on this project here, and we have around, in a GPU, around 1 million steps. We can do around 10 or 20 nanoseconds per day in a GPU processor, and then we can perform around 40 or 40,000 or 100,000 atoms in the system. And we can see that depending on how long we need to simulate this system, we can spend around 30 days or 120 days working in a GPU processor, okay? If we take this calculation down the CPU, you are around 10 or 15 times slower than you can do it in GPU. Okay, so then to perform molecular dynamics in a very large system, it's very important that our machine has GPUs, because we are going to speed up with this kind of procedure. And if you wanted to study all the details about the molecular dynamics, Monte Carlo, we have very nice books. I can at least suggest 5 good books that you can read, understand, see all the approximations, methodology, and so on. So people are telling me that I have only 5 minutes, and then I will not have time to go on and talk about more details, but I will start to give more details about molecular dynamics now. And I'm only to show that with the classical force field, you can deduce the analytical form of your force. So in the classical force field, you have analytical equations for calculating the force. You do not make the numerical derivation, but analytical one. You can use that. You have other algorithms, like I spoke before. Here you have the velocity with the square of the time. But also you have the leapfrog. You see, this is the true equation. And now we do not have the dependent on the time square. We have only 2 equations, but without only the dependence of the interval of time. So this kind of methodology you can use when you go to a smaller delta t, but then you calculate velocities and positions in different times. When you apply all the calculations in atom, in one single step, you calculate the forces of each atom. Each atom has a different position. It means in one step of the dynamic, you change the center of mass of the molecule, the orientation, and the deformation. Everything moved together because you have an atom interaction, okay? So then you are considered the internal degree of freedom. Typically, you can use 0.1 femtosecond of time, but if you freeze the movement of the hydrogen, either put it together with other atoms or make the bond of the hydrogen with, can increase this number from 0.1 to 2 femtoseconds. So you are making your simulation 20 times faster if you make only the hydrogens fixed, okay? So you have methodologies that you can fix the distance, but take attention that all algorithms, all of them, they move the atoms freely, and then they correct the constraints. So if you put constraints, you are increasing your computational time. Better if you put constraints in less parts of the molecule that you want, okay? So I suggest never use, for example, rigid geometry of water. You take much longer of your simulation to make the water rigid, then leave the water move. What you can do to make your program speed? Make the bond of OH fixed. So you only fix the bond, but leave the angle, okay? So this is my suggestion. And then you have also several kinds of thermostat. In the literature, you can find at least 5 different methodologies that you can apply for the thermostat. You have in all the thermostat advantage and advantage because all of them use approximation that are more strong or less strong. And you can find papers where they compare all the thermostat and show you what's the advantage and advantage for all of them. Actually, the most used methods are the nose-hoover thermostat and the Berensen thermostat. And the Berensen has only one problem, is with the ergodicity with the canonical ensemble, because the Berensen thermostat shows you that you should reach a temperature that you desire with exponential movement. And you put a coupling that can be strong or soft. Depending on the coupling, you go fast or you go very slow. But when you reach the temperature, your fluctuation depending on the coupling. So you are going to have the wrong fluctuation of the canonical ensemble. And that's why people put here some random movements coupling to the Berensen. It calls velocity Verlet, and this one is the most used methodology to have the thermostat, okay? So here I'm presenting this idea. I have the Berensen thermostat here. I can go very slowly, and I have small fluctuation. I can go very fast. I can go very slowly to the temperature, but then I have a large fluctuation, and I can correct that using the velocity Verlet. Also, if you decided to use the noise groover, is a well-known and well-accepted movement, but it also has problem. When you start with a temperature that is far away from the target temperature, your system go oscillating. And these oscillations in the beginning are very high. So I suggest that you always use velocity Verlet thermostat in the thermalization, and after your system are thermalized, you can move, if you wish, to noise hoover. Otherwise, stay in the velocity Verlet, okay? But do not start your simulation with a temperature that can be far from the target with the noise hoover, because you can have several fluctuations in the system that can make trouble, okay? You can apply the same methodologies for temperature, for the pressure, for the barostat. Only think that the pressure is not a scalar, is a tensor. So you have a much complicated algorithm that we're going to deal with the change on the box size to have constant pressure. You can have isobaric, all the sizes move together. You have an isotropic, that the two sides have different from the other, and completely anisotropic. Isotropic, semi-isotropic, and anisotropic. So you can change the form of the box depending on the system that you put, or the coupling that you put between pressures. And you also need to have the periodic boundary condition, because you have interaction with the box. In general, we use periodic sense. You are going to implement the cutoff radius, meaning that you are going to select a radio here, and you are going to make interactions only inside the radio. If you think about the volume of a sphere inside a cubic, you have 52% of the volume. It means that you have a lot of computational gain when you include the radio, the cutoff radio. And if you have a cutoff radio, also you can improve your simulation, use the neighbor list. It means that in general, if you are interested in calculating the forces of one particle, you are going to interact with all others, asking if this new molecule is inside the cutoff. This is with no approximation. Other approximation that you can do is make the list of the neighbors, and when you do the loop only in the list. So you save the amount of calculation that you are performing if you include the neighbor list. So in the input, you need to say, I need the neighbor list, and I need to actualize the neighbor list. Then that's why you wait a little until the movement of the molecules. In general, you have a buffer of the radius. That's almost the displacement of the molecules. Then you put all this together and have a neighbor list. I'm showing here only if you wanted to take idea how you gain in computational time. Here, this is a size of the system. If you have a system, for example, in this case, I have around 100 water molecules. I have around 66,000 atoms to interact. If I calculate amount of interaction for each step, I need to have around 2 billion per calculations to calculate the forces, okay? If I include a cutoff radio of 14 angstrom, this is what people uses. You calculate a radio, your interactions reduce to 100 to 1,200 sites, and then you decrease it for 1 million calculations for calculating the forces. So you are having a gain of 99.97% of the calculation, if you use or not use the cutoff radio. So you need to use. You have no choice. So then you need to take attention, because when you cut, you generate discontinuity in your potential, and you cannot derivate on the discontinuity. You need to adjust your potential in this part. And also understand that the cut in the Lennard-Jones is not relevant. The relevant is the cut on the Coulomb term. You have to make approximations in how to adjust your system here in the cutoff region to do not have discontinuity. In general, you have two methods, one that you sum a function, the other one that you multiply a function. You can choose the method that you want. You can also use the van der Waals, the Ewald sum. It means that you are going to make interactions of your original system, perform replicas of your system, and calculate this sum. You have several difficulties to make the direct sum of this function, because this is not a symptotic convergence. What is a symptotic convergence? Is when you guarantee that the next term is smaller than the previous one. With this sum, you have no guarantee. The second term can be larger than smaller than larger again. So if you have that, you never know where you should stop. You need to follow until infinity, the sum. Okay? Then you have several forms to do that. And the idea of Ewald is, if you have distances and charges, you can describe that by delta functions. You are going to screening these interactions, subtracting Gaussian distribution that has a width and intensity with the same position on negative side. So you are going not calculate on this, but on this screened distribution. And if you summed what you subtract what you add, you cancel and you have the same. So the idea now is that the first part, you are going to sum on the real space with real positions. The second part, this is the other one, the cancellating distribution, we are going to sum in the reciprocal space. When you do that, I'm going to finish. When you do that, you speed up your sum. You can sum until infinite. You can do this as this is a continuous distribution, as integration. This is the Ewald. But if you discretize your system, you use this particle mesh Ewald with the sums. So if you are working with charged system, you need to use that. You cannot avoid it. But one point is that all boxes should have the total charge 0. Because if you do not have, this sum is divergent. Okay? That's why you need to put counter-ions in your system to neutralize the total charge. Or if you are working with ionic liquid, you have always a positive and negative part. Okay? So I try to show here several parts of the molecular dynamic. If I have more 1 hour, I will speak very slowly, showing the details of each methodology, so advantages and advantages of each one. I do not have time, so I leave here the slides. Who want to follow? I have references, books where you can follow, and perhaps next school, if we come back to this subject, I can talk more. But here I'm invited people who wanted to participate. Me and Professor Arnaldo, we are organizing this school that's going to be here in São Paulo in the end of October, and this is the topic. Who wants to apply? There is an inscription there, and we are going to support 20 participants with the CAPES money, okay? So if you do not have a grant to participate, but you wish, please apply there. If you have your own money from FAPESP, good, we accept you also. So thank you very much.